Okay, good morning, everybody. And I'm here. It's my pleasure and honor to really moderate this panel. We have a very distinguished panelists. There are very few times you get two Turing Award winners on a panel. And we have really a breadth of expertise here from supercomputing to quantum computing. And we are going to have a little bit of a controversy between the future of supercomputing versus quantum computing. Just to give you a sense, we really had a very fun conversation for the past 1 hour or so when we just met up. And I really wish we could record that and show it here because it was really very, very interesting. And I hope some of it will come out again in the panel discussion today. Uh, so today's panel is about supercomputing and quantum, redefining the future. Supercomputing for the past few decades have really been the cornerstone of scientific innovations, and really we have reached at a stage where we are at exascale level, where if you are just wondering exascale, it's 10 to the power 18 floating point operations per second, which just seems mind-boggling. But at the same time, we are seeing AI sort of coming in, and the future of supercomputing versus machine learning infrastructure. That's an interesting conversation that we are going to have. At the same time, quantum computing is emerging as a really promising solution to many problems, but people have a lot of skepticism around that as well. So we are going to talk about all these issues today. And please allow me to introduce our distinguished panelists. So starting from the left, Professor Adi Shamir. Uh, uh, Professor Shamir is the Paul and Marlene Borman Professorial Chair of Applied Mathematics at Weizmann Institute of Science. He's really the father of modern cryptography. All of us have used RSA, public key cryptography algorithm, so the AS stands for Professor Shamir. And more recently, he has been working on zero-knowledge proof for identity authentication. He is the winner of the ACM Turing Award in 2002, the highest honor in the field of computing. 1996 Paris Kanalevsky Theory and Practice Award, 2008 Israel Prize for Computer Science, and 2017 Japan Prize. He is a member of several scientific academies. Please welcome Professor Adi Shamir. Next, we are very fortunate to have another Turing Award winner, Professor Jack Dongarra, who specializes in numerical algorithms in linear algebra and parallel computing. And really the software algorithms and implementations that he had developed contributed tremendously to the extraordinary progress in computing performance and application. He holds joint appointment at University of Manchester and University of Tennessee. He is the winner of the ACM Turing Award in 2022 for his contributions, fellow of ACM IEEE, CM, IEEE, and a member of many of the academies. Please welcome Prof. Dongarra. Okay, so now we move on to our two quantum experts here. First is Prof. K. Nemoto. She is a professor at the Okinawa Institute of Science and Technology, where she directs the Center for Quantum Technologies, and also a professor of Japan's National Institute of Informatics. And her research interests are in quantum computer architecture, fault-tolerant quantum computing, quantum machine learning, as well as quantum networks. She leads many of the major national and industry academic initiatives in quantum information science, and she is a recipient of the Japan's Best Science and Technology Award and was appointed to the French National Order of Merit in 2022. So please welcome Professor Nemoto. Then we have Dr. Patricia Lee. She is our industry expert in this panel. She's the chief scientist for product technologies at Quantinuum, which just recently set up a shop in Singapore. And she leads the technology roadmap effort to scale up trapped ion quantum computers, and for which she is very, very well known. And she worked at NIST and US Army Research Laboratory before joining Quantinuum. Please welcome Dr. Ali. And last but not the least, we have Professor Torsten Hoefler. Interestingly, he is the winner of the, is it ISC Jack Dongarra Award? So it's really interesting to have both of them here. His research interests are in performance-centric systems design. He's a professor at ETH Zurich, a member of Academia Europa, and fellow of ACM IEEE and ELIS. He's the winner of the 2024 ACM Prize in Computing, which is one of the highest honors in the field, in addition to many other awards. Please welcome Professor Hoefler. Okay, so the way we will go about doing it is that first we will listen from the experts in supercomputing or classical computing. What are the challenges in this area? Where do you view that field to be in the next decade or so? And what are the applications potentially that could be enabled by this? So maybe we can start with Prof. Dongarra.
So thank you. Let me just start by trying to identify what we mean by supercomputing. So in this context, we're talking about scientific computing that's done on the fastest computers that we have today. So the definition of supercomputing changes over time as the technology evolves and provides us with better ways of doing things. When I started computing 50 years ago, the computers that were called supercomputers were vector computers. That is, they use vector operations to carry out the basic things, and that was their secret sauce in some sense. They were specialized computers that were built specifically for scientific computing. And that has evolved over time. It's evolved because of the technology changes. Moore's law, everybody knows something is doubling every 18 months. It's slowing down, but that propelled us in certain ways. There was Dongarra scaling, which helped in terms of getting the cycle time and giving us basically a free ride in terms of turning up the cycle time and using less power. And we went from vector machines to parallel computers. Those parallel computers had shared memory, and those machines evolved to distributed memory parallel computers, to things that we call massively parallel, which had, at that time, thousands of processors in them, to today where we have computers which use accelerators to boost the floating point computational rate. So the floating point rate is what we usually use in scientific computing to measure the performance of our applications and of our computers. And we're talking about 64-bit floating point operations. That's the fundamental way of doing an add or a multiply on these computers. Sometimes we can get away with 32-bit computations. If we go to 32-bit, we get at least a factor of 2 in terms of performance. Things run twice as fast because there's twice as many operations being done, and there's less data to pass around as well. You have 32 bits of data instead of 64-bit. That really helps to boost the performance. So we see changes taking place, and those changes have dramatic impacts. Today we have evolved to using machines which are a hybrid. They have multi-core processors, which are commodity processors, together with accelerators. And those accelerators are in the form of GPUs. So graphical processing units have been used or taken and stuck in our computers to boost the floating point computation rate, to give us machines that run today at 10 to the 18 floating point operations per second. That's a billion operations per second, 64-bit floating point operations. That's an incredible number. I have a hard time getting my hands around that number. The total number of seconds since the Big Bang is about 10 to the 18 seconds. So it's an enormous number, and that's the number of floating point operations that can be performed in 1 second. So incredible changes in terms of the architectures have allowed us to get to that point. We usually think about floating point operations as being the things which slow down or take the most time on a computer. But it turns out that today, it's not the arithmetic that takes time. The arithmetic has actually, I think, been over-provisioned on our computers. And the thing that takes the most time is moving data from one place to another. So data movement has been the critical resource on our computers. And these computers, of course, use tremendous amounts of power. So our biggest machines that are used for scientific purposes, they run at exaflop, 10 to the 18 floating point operations per second. They cost about half a billion dollars to purchase, and they have a power consumption of about 30 megawatts. So 30 megawatts, what's a megawatt? So if I use a megawatt at my home for a year, I'll get a bill from the electric company for $1 million. So in the US, in the state of Tennessee, that's what a megawatt year costs. So this machine that we have, one of the supercomputers, is roughly $30 million to use for the year, 30 megawatts, just to turn it on. And the machine, as I said, cost about $500 million. And there are a number of these machines in use around the world today. They're being used to solve some of the most challenging problems. They're being used to solve a single problem at a time. That is to say, the intent of these machines is not to be split up and to run thousands of jobs, although most of the time they're used for that. They're intended to be used to solve single heroic computations that are run across the whole machine and may consume days of computational time. So important problems are being solved. One of the big issues here is developing software and algorithms that can use that number of processors. So we're talking about 10 million processes running on this computer. So if you're going to program this machine at scale, you had better be prepared to orchestrate 10 million things at a time to get them to work in parallel and to compute the computation that you have. And today we're seeing sort of this morphing of scientific computing with AI. So they both play a very integral part of doing scientific computing today. So it's really, HPC is being used to drive AI, and AI is being used within our applications to help us get to a solution in a much better form. So I'll stop there and leave some time.
Thank you very much. Adi, do you want to?
So my field of research is cryptography, and there's always been very interesting connection between supercomputing and cryptography, because many of the big advances in building larger and larger machines had been in governments wanting to break the communication, secure communication of other governments. So this is the reason why they're spending billions of dollars on building those huge machines. I want to point out that with today's crypto systems, for example, the AES that I mentioned in my talk earlier today, the size of the key is 256 bits. So if you want to use supercomputers in order to exhaustively look for the correct key among 2 to the 256 possibilities, even the largest available supercomputer or even the largest conceivable computer will never do the trick. So the advantages of supercomputing had been enormous during Second World War, during the Cold War period, when keys were shorter, when you could use all kinds of shortcuts in order to reduce the complexity of exhaustive search. Today, your ability to break top-level communication using supercomputers is diminishing. So today, I would say that the main users of supercomputers had shifted to the Department of Energy, simulating nuclear explosions when you cannot do a real bang in the atmosphere. But people in the NSA, etc., are still using supercomputers, but not in order to directly break the crypto system to do all kinds of other nifty stuff.
Thank you. We could go back later to whether quantum can break that, but before that, maybe, Torsten, you want to talk about your work in optimizations, and how do you see the performance optimization and reducing the energy for the HPC system that we talked about earlier?
So yeah, thank you, Tulika. Yes, I would like to continue the story, so to say. We went from the history of supercomputing, what is a supercomputer, to one particular application, breaking cryptography, which is tapering out as we heard, and then the last thing I heard was nuclear weapons. Well, okay. I believe supercomputing has a much wider application area, which indeed helps us as a society to move forward, designing new drugs, designing new materials, discovering all kinds of interesting things in the traditional scientific computing area. Now we've already heard that in AI, this is also aiming at that discovery, at that scientific discovery. So now we have this interesting bridge to carry, but I want to focus more on the optimization like you suggested. So where Jack stopped was we are now at today where we have accelerated systems, but what does it actually mean? Why do we have these accelerated systems is the first question. Why didn't we just continue to build normal GPUs, or sorry, normal CPUs? The reason for this is because, also Jack alluded to this, Moore's law, all the nice lower scaling stopped. So we don't just wait and get a faster processor next year. This is as computer architects. So what we had to do in the very recent past, in order to gain more speed, gain more efficiency, reduce the energy consumption, reduce the carbon footprint of these machines, we had to change the architecture. There were two fundamental things we changed in the architecture actually to move forward. One is a very simple one to understand. There's reduced precision. So in the good old days, the scientific computing folks, they came up with equational hypotheses. So very smart people developed the fundamental equations of society today, fast Fourier transform, or fundamental mathematical techniques, fast Fourier transform, Hamiltonian simulation, that's a very simple equation, all kinds of things, Eulerian equations. And these were thought to be precise. We were always assuming we must solve these equations precisely. So when I run a climate simulation, for example, I solve the Navier-Stokes equation in the atmosphere. It's a flow problem. But we always thought we need to solve this in FP64 for all kinds of different reasons. But now the new big use case is AI. AI does not have a compressed representation such a simple equation. I cannot explain human knowledge with a simple equation like the Navier-Stokes equation. So I must go to statistical methods, at least the best tool we have today to learn. We learn the statistical distribution of language on the internet. That's the best tool we have, but it's a statistical distribution, so what does that mean? It has error bars. It doesn't require FP64 computations because we don't even think it would be accurate. So what did that lead to? The specialization in these machines, they gave up on accuracy. Jack said we could get away with FP32 for a while. That's absolutely true for these absolutely accurate equations. But to do the statistics that we need to do for machine learning, FP32 is total overkill because the noise in that data is significantly higher than the noise margin of FP32. In fact, the natural noise margin is somewhere in between FP8 and FP16. So now what has happened, of course, there was a bigger market in high performance computing, that is AI, and now everybody builds these AI accelerators with reduced precision. So now, unfortunately, the scientific computing field has to be reactive to it. It has to somewhat adopt because suddenly all the machines had lower precision, at least the performance of lower precision. I see this as an opportunity, as a benefit, because by lowering the precision, we reduce the energy consumption, we get more compute. So we had exaflop. The first exaflop machine was not an FP64 exaflop machine. It was an FP16 exaflop machine because you get naturally more than 4 times as many FP16 operations for the same equivalent of FP64 operations. Why is it more than 4 times, actually? It's an interesting one. Most people say it's exactly 4 times because, well, 64 divided by 16 is 4. Yes, but the multiplier unit is of quadratic complexity. So you gain a little bit more than linear. So it's a little bit super linear. It's not much. It's like 2.1 or 2.2. But that should not be forgotten. So that's point number 1. The second point, also Jack alluded to, is that actually counting operations today is not very useful, unfortunately. Unfortunately, that is a problem because that's what all of us learned in school. That's what we are teaching in school. We learn to count operations. When you learn algorithmic complexity, you count operations. When you talk about matrix multiplication, you learn that the trivial matrix multiplication algorithm of an n by n matrix consumes n cube operations. Most of you will not learn what the data movement is that is required to do this. to perform this computation. Jack already said that the data movement is much more important than the computation. In fact, many people say computations are nearly free today, so it's all about moving the data to the right location, but nobody teaches that at all. Zero. I mean, I'm teaching a little bit. I'm changing my lecture to include I/O complexity, but I/O complexity is incredibly complicated to teach. We don't understand many of the concepts for this, so I would like to encourage you, as the next generation, to actually think about this and help us to get out of that hole. Because right now, we are in trouble somehow. We count operations. We teach our undergrads to count these operations, but this is wrong. You shouldn't design algorithms that minimize the number of operations primarily. You still should minimize the number of operations, of course, because it has a nice side effects. Typically, when you minimize the number of operations, you also minimize the data movement. But it would be much better to primarily minimize the data movement and then care about the number of operations, because you can invest operations for data movement. You can trade those off, and it's much better. So that's one of the things I would like to give you as the audience to move forward. And now I can give the word to the quantum folks.
Thank you very much. So from the classical supercomputing and high-performance computing, so what we heard is that these are highly scalable system, right? So we have reached exascale level. We have systems where we are now struggling to develop the software and manage these systems at this point in time. And then we are moving towards the AI hardware, which does not really require the kind of precision and accuracy and numerical stability that high-performance computing depend on. And so that's certainly an opportunity. And Torsten talked about how the numbers are not really important, but really how do you manage the data, how do you move the data, that's becoming very important. And I think that makes the perfect segue into the quantum computing space, because I think quantum computing at this point in time is very much of an experimental way of dealing with things, and you were still talking about number of qubits. And so I would invite Patricia and Kay to talk about how you view quantum computing today and how you view quantum computing's impact and potential in the next decade or so. And when do you think you can actually reach the level that supercomputing today, classical supercomputing today, can offer us in terms of scientific discovery and things like that? Yeah.
Okay, so quantum computing is a little bit difficult to summarize at the moment because there are so many different views. But if that's supercomputing, you say it's a fully grown giant, the quantum computer is like just a newborn baby. So, so cannot walk properly, cannot eat properly, it's a quantum computing. We can do certain things, but it doesn't work as we want and still have errors, and there are lots to room to grow, basically. So it's also difficult to predict what would happen and how we use quantum computers in the future. But it is true, we have seen the history in the 2000s, around 2000s or sometime before 2010, up to that mark, or even this, before Google's 54 qubits paper came out. Very sort of sophisticated people in the field, both computer science and physics. Some people said, oh, quantum computer wouldn't happen. Wouldn't belong to this world. They are very easy to say negative things about it, but we broke that through. Actually, 50 qubit was our dream number. And lots of people thought, well, 50 of qubits that's working quantum mechanically at the same time wouldn't be possible. And quantum error correction, that works only on paper. But we have all demonstrated how actually it works. So it is very difficult to predict, this kind of, we're changing the principles of how we encode information in a physical system. After all, the information is physical, right? So, but then now the notion of information in quantum computation is different. So we are changing. Of course, there are lots of different ways, like chaos computation, DNA computation, natural computation. There are lots of computation, of course, people thought about. But quantum computation is unique in a way we change the notion of information. And another interesting to the future is if we are successful developing quantum technologies. It's not only quantum computers. We have quantum communications, we have quantum sensors, we have quantum emulators, or whatever like this. It's coming into quantum regime. And now output signal will be quantum signals. And how do you process that in classical computers? That's very sort of waste of the resource. We want to have the quantum signal input into the quantum computer and process it. Because if you measure the state, if you measure the output, you will lose almost the information that state output has. So in that sense, quantum computer might have a completely different world. And that's kind of interesting, but also worrisome. Because now there are quantum computer and another quantum computer is connected, like the data we can move around quantum mechanically. Well, but we don't know what they are sending to each other. Because if we measure it, we will collapse the state, right? So then there will the database, maybe one computer calculated the answer and stored in the quantum data center. And well, machine hold that, we don't know. So it seems like there's another layer of sort of quantum data, which we cannot really touch, and it will be supported, of course, by the classical computational systems. But that kind of things, we never thought of it. Of course, that's won't be happening probably in my lifetime, because there are lots of difficult things to do this. But quantum computer technology could have that kind of potential. And that's probably something really interesting to think about in the next generation.
Thank you very much.
Yeah, I think there's so much development in quantum computing in recent years. Obviously there's a long history from, Shor's algorithm in 1994, but also even before that with Feynman and sort of Deutsch-Jozsa and all those dreamers, people who came up with the concept. But really, since 2019 was when Google came out with a quantum supremacy demonstration, where they claim their quantum computer can do these random circuits that classical computers cannot really calculate. And even though these are random circuits, it does show that there is some computational space that is beyond classical computer. Now, in the intervening years, right, 5 years later, I think the Chinese superconducting groups have developed a new algorithm, classical algorithm, to better simulate that classically, and have to build a whole new supercomputer just to actually beat the Google result. But in that intervening 5 years, Google's quantum computer got better. They got more qubits, more precision. And so their recent the demonstration with 105 qubits on the Willow chip, there's no doubt, nobody has ever claimed that they can actually simulate that classically. Similarly, on the trapped ion side, we've also developed, that's what I worked in, we've also developed our system and grown it to the size that our latest system is 98 qubits. And in fact, we're building one in Singapore right now. And that system has even better precision than Google's Willow quantum processor. And again, we also have all-to-all connectivity, which makes it even harder to simulate classically. And so we can also do these computations that classical computers cannot cannot compute directly. And so there's a question of is this really useful? Because there is definitely this computational space where the quantum computer can execute circuits, quantum algorithms, quantum programming that classical computers cannot. But the question is the problem you care about, right, people care about, can be solved in that new computational space that we never had access to until recently. And so people are developing algorithms. I think there are a lot of advances in quantum simulation, which is a lot of the scientific computing problems, in terms of looking at superconductivity, quantum magnetism, nuclear physics, neutrino oscillations. And these have all been implemented on our quantum computer. They are in this, I would say, gray zone of quantum advantage, in that you can't just use a classical computer and run the same quantum algorithm and get the answer, because it's already beyond what classical computers can do. But there might be some approximation methods, right, that could get you the same answer on a classical computer. And then that takes a lot of nuance. And exactly, is this calculation in that regime of where it's classically, you can classically compute or not, and then how much classical computing resources you need to actually get the same answer as your quantum computer, how much power consumption is that going to take, and how much time is going to take. And right now, it's, I would say, many of the demos are in a race in that in that situation, because you do a demo on a quantum computer, maybe somebody, was very clever, came up with the algorithm that can produce those results, months later after you publish your answer, your results, and then, we then do something else different.
Yeah.
And so that's where it is. I think it's very interesting times we live in, and there's a lot to explore on how we can utilize that extra, computational space we now have in quantum, and that space is only going to grow as the technology develops.
Okay, thank you, Patricia. I think, Adi is ready to.
So I want to tell you where I stand. You can call me a quantum skeptic. I fully appreciate the hard problems that had been tackled and partially solved so far in getting to quantum computers. I want to remind everyone that there had been many attempts to unseat the long-proven technology of silicon-based supercomputing. We have been using silicon-based computers for the last 60 years or so it has a huge advantage. It had been perfected for many, many years. People have tried to invent all kinds of alternative architectures, for example, optical computing. You're using a very large number of photons and photoreceptors in order to try to perform matrix multiplication faster, etc. So all those earlier attempts to unseat silicon-based computing had failed because either they failed for some technical reasons, or they at least didn't offer large enough advantage. Looking at quantum computing, in order to unseat, to replace our regular computers, they'll have to demonstrate a huge improvement over all the accumulated history of silicon-based computing. And there is only one application, or maybe two applications, but the main one is using Shor's algorithm in order to break RSA. Now, this is, in reality, the reason that most governments are spending billions of dollars on quantum computing. I know that many physicists are coming to me and saying, thanks for inventing RSA, because that's why my government is spending so much time on me doing quantum computing. But jokes aside, this is a self-defeating kind of endeavor. Why? Because the very fact that we all know that RSA may be broken, I don't know if it will be 15 years from now, 30 years from now, but we know about this possibility. And therefore, anyone who has or had already over the last 20 years had serious secrets, strategic secrets that it wanted to hide, didn't use RSA alone. It either used some other algorithms or a hybrid RSA plus something else. So for the last 20 or 30 years, the major governments had been moving away from pure RSA encryption. And as a result, I think that after spending the billions of dollars and all this big investment, governments are going to be disappointed to discover that once they put their hands on the quantum computer and they start breaking the keys and recovering communication, they'll have very little strategic advantage in learning the deep secrets of their opponents because they've stopped using it long ago. So quantum computing, the fact that it exists makes it much less attractive if governments thought about it this way.
Let me just add just a short thing to the comments that I don't think quantum computers are going to replace our digital computers. That's clear to me. We're not going to have a quantum supercomputing and we're going to throw out the old one. We're not going to have a quantum laptop and throw out our laptops. That's not going to happen. Not anytime soon. Anyway, not in my lifetime. And I see what I do see is a quantum computing being put in a supercomputer in terms of a node on that supercomputer. So if you need the function that the quantum computer can provide, you can get access to it through the conventional processing. And not only will it be quantum computing, but there could be optical computing added on to this ensemble as well. A neuromorphic computing, perhaps DNA computing. So we see it fitting into a sequence that we could assemble, dial up perhaps, to do the kinds of calculations that we're interested in pursuing.
So I'm usually the quantum skeptic, but I'm less skeptic than Adi. So I would say there are more applications than RSA for quantum computers, but I'm really concerned about the number of applications we know today. So I totally agree there is this space that is incredibly powerful. That space goes back to Feynman's original statement about a quantum computer. That space is known to us and to all our best mathematicians longer than the existence of the state of Singapore. So that space is significantly older than 60 years, and we have a very, very, very limited number of algorithms today that would take advantage of the computational power in that space. We have the random circuit, okay, but I don't care, nobody cares. I mean, it's a nice demonstrator, I agree. Maybe not nobody cares, but none of us really wants to solve a random circuit problem, that's useless. There are some computational science problems that are really nice, especially if you have small band gap, if you're a chemist or a physicist. There are some problems that are physically or classically very hard to approximate, but quantum computers can really help. If you're a computer scientist and you believe that quantum computers will solve P equals NP, forget about it. It's not going to happen. Well, very likely, of course, we don't know if P equals NP, but it's very hard. So it's not obvious that you can do this search. So I'm a little bit concerned about the fact that I've seen so many smart people work on trying to make use of that space on paper without having a real machine. And all they came up with is the original Feynman thing that is simulating quantum physical systems, essentially, which, I mean, this chair is a quantum physical system, so obviously I can simulate that chair well in all kinds of materials. And QFT. QFT is the underlying strategy that allows to work in nice number theoretical groups, and then unfortunately, RSA is based on this number theory, and so yeah, that you can break, but we know there are better algorithms that are not as easy breakable. So that's my major worry. So we need, again, the call to the audience. We need smart people. I wouldn't dismiss quantum computing, but we need smart people finding more applications, what we can actually do with it. And I personally believe that having a working machine will only get us so far to play with the thing. Many people claim that once we have a quantum computer, we will just code things on it and it'll just do magic, and suddenly we will make big algorithmic advantages. This is not really how it worked in computer science when we invented the big algorithms. Usually smart people came up with a good idea what the algorithm should do, and then we implemented it on a computer. Again, in quantum computing, we've been trying this for 60 years. So that's the challenge.
So Patricia, would you like to respond or?
Yeah.
Okay.
So I think when Jack said that for supercomputers, right, there's always a demand for more scientific computing. And I think for quantum computers today, it's the same simulation, it's the same type of computation that the people are using supercomputers for, right? And that demand is there, right? The fact that governments and entities fund supercomputing and high performance computing there's no, if quantum computers can perform better or perform cheaper in terms of energy consumption or other metrics, then there's, presumably that people will still be interested in the technology to, I'm not saying replacing supercomputer, right? I'm saying obviously the quantum computers are controlled by classical computers, so that can't be replaced. But it's this hybrid, right, where maybe some problems are better solved with classical computers and some problems are better solved with quantum. And so you take advantage of whatever tool is the best for your problem set that you're interested in. And then the other thing I think is very interesting about precision that you were talking about is that in quantum, we always had this idea that if it takes certain number of operations, right? If it takes 1 million operations, then you need the precision of 10 to the minus 6, which is hard to get. But for certain types of problems, like condensed matter systems, where the system is inherently robust, right? We know that materials are defects, there are imperfections, yet somehow it still behaves, in very similar properties with a few defects here and there. And so, in fact, there are papers that have come out just in the past year or two that says that, well, yeah, a lot of these simulations actually doesn't require, the 10 to the minus 6 precision. Maybe, 10 to the 3, 10 to the minus 3, 10 to the minus 4 precision is sufficient, right? And we can get a good enough answer. And sometimes good enough answer is good enough for people to go and do the physical experiment, right? And so we're back to it's the same thing with the loss of precision on the classical side.
I don't want to fly on a plane which has that precision.
What?
I don't want to fly on the plane which uses that precision. I need to have more.
Right, but I think it's for scientific calculation, right? It's not saying that you're relying on that to fly a plane. And we're saying you're relying on that to build your scientific understanding and intuition to go and discover the actual material that works that way, and then you can do all your physical experimentation, and then use that for whatever purposes.
Okay. So I think we have agreement that we are not going to move to quantum only, right? So it would be some form of hybrid, but I think our supercomputing experts are a bit skeptical about even that happening, and thinking that government is spending all the money for the post-quantum cryptography, and maybe we have already sort of moved away from RSA, so that's a moot point. But I think that this is a good point for us to open up this for the audience questions. So I think there are microphones on both aisles. So if you would like to ask a question, please come forward, introduce yourself, and then ask the question. Yeah, please go ahead.
Thank you for the insightful discussion. I'm Sebin Abraham, a fourth-year PhD candidate from Texas A&M University. I had a question from a biological perspective. Dr. David Baker's lab has been focusing on using Rosetta and other platforms for protein structure prediction, but they mainly rely on the native state of protein. Mimicking the exact cellular conditions or incorporating post-translational modifications in a disease perspective is still a main challenge. So do you think we could incorporate quantum many-body simulations or quantum walks and address this concern in the near future?
I will admit that I don't know, right? And these are things that people haven't looked, people are looking into right now, right? How do you translate a problem set, right? Which in your case is looking at proteins and all the interactions. How can you represent that, right, in a quantum in a quantum circuit? Are there algorithms, known quantum algorithms that are applicable to solving those problems, right, once you have it set up? And then how does it translate into the actual programming and the actual execution on the machine? And then the question, of course, is are the systems today sufficiently large or sufficiently high fidelity, has the performance to actually go and execute those circuits? All those steps, I think, have just not been explored, right? And that's very active areas of research for a lot of people, very exciting times, and I think definitely worth looking into.
I can say that if it will be done, it will be on the third generation quantum computers, where the first generation is many, many years away. So
So I also don't know, but I think it may be unlikely because there's one thing about quantum computers that is fundamental that we know. Nobody has said this yet. So a quantum computer is a device that can only read very little data, fundamentally, unfortunately. And it can only output very little data because every time you sample, you collapse your quantum state. So that you need to keep in mind. So if you believe you can solve big data problems with quantum computers, it's most likely not because you cannot ingest big data. We have no QRAM is very, yeah, we can take that offline. So-
actually,
so
this is
that-
not a
it
big
has an
problem.
input-output problem, the machine.
But
This
I
is
think
not a big-
there's, I'm sorry, I think there's a question of how you input the state, but if you look at how you set up your starting point, right? If I have a quantum state and I want to enter it, I don't have to enter it one by one, right? It's finding the operations that go and build those states, and actually, some of it could be efficient, because depending on your data set, right? That because if you have a fully entangled system, a very large fully
Absolutely.
entangled system,
Look,
there may be clever ways to do that.
Very
And
simple
people
argument.
are looking at how to implement,
Absolutely.
how your starting point, your
What's
starting data point.
absolutely very simple argument. The near-term quantum computers will have megabyte per second at most.
So
So what does your current computer
Well,
has
what does that
as,
mean,
as an
megabyte?
input band?
I think
How
we
much
have
can you read into your computer?
98 qubits, right? Already has, right, 2 to the 98.
I'm inputting. Yes, your state is 2 to the 98, but you cannot read the data into that state. What is your input bandwidth from classical bits into quantum bits? Can you give me that number?
It depends on what it is, right? And
No. It's just reading the data. How many bits per second?
it's not as straightforward, because when you put in that data, right, you have to find there are methods of either unitary operation to like put that into it.
How many
right?
bits per
Or
second can you read from classical into a quantum
I
state?
think that's a classical way of viewing the problem.
Yeah,
Right?
it's
Because the
classical
quantum
bits.
is not the same, right?
Okay.
And so there are ways that you can do feed forward,
Move on, yeah.
and there are lots of papers on exactly dealing with that problem.
We live
right?
in a
And
classical
So
world with
I think
classical
you are
bits.
viewing what we had, when we had the private discussion. So, but, in order to give an opportunity to the students in the audience, so maybe the next question, yeah.
Thank you.
Thank you. I'm a postdoc doing medical science topic from Taiwan. I'm going to ask naive question again. So my first question is more related to the role of quantum computing in modern computer science. One in computer science, one issue is moving data, because moving data consumes a lot of energy. And my first question is, why don't we just put the GPU, RAM, and CPU all in the same place, so we can prevent moving data from these between these places? And my follow-up question is, can quantum computing help this data movement consuming issue? And if I interpret this correctly, are the operations in deep learning networks too precise? And how can we solve this at the beginning to prevent the calculation process from getting started in the local minimum? Thank you.
Thank you. So if I understand, the first question is the data movement between CPU and GPU, and then can quantum solve that problem? I think that's the discussion that you were having earlier. Torsten?
I can be fast. Yeah, it's a very good question. Unfortunately, if you Oh, okay. Well, unfortunately, if you distribute your computation, if you parallelize your computation, you must move the operands to different devices, different compute localities, because you compute in real space. So you must move the data around, and that's an unfortunate fact that we just need to deal with. It's an interesting fact, though, if you look at the details, but I'll keep it short. And then for the quantum thing is again the question: how do you go from classical, because we live in a classical world, to the quantum world? And again, this is very limited, this classical to quantum, but once you're in quantum, and this is probably what you meant, you have humongous possibilities. But we live in a classical world, so I somehow need to get my bits in, and I still didn't get an answer what you meant with this.
Yeah.
So if your question is a distributed quantum computation, and of course, if you have two processors, quantum processors, and if only communicating classically, then you cannot power that up. You have to have quantum communication between them. And you don't necessarily need to move the data from one chip to another. You could actually distribute gate as well. So there are choices how you operate your distributed system.
Thank you.
Thank you. Yes, please go ahead.
Hi, I'm Deepika from EPFL Switzerland, and my question is actually to all the panelists. So if you have unlimited computing power one day, which is not limited by hardware or software or algorithm, what would you use it for? Something that has not been possible today. I mean, I understand it's difficult to predict the future as mentioned by Professor Nemoto, but is there something that you would like to manifest?
Okay, that's an interesting question. Yeah.
I would like to solve some deep mathematical problems using this unbounded computing power. I can give you many examples of well-known problems, Goldbach's conjecture, Riemann hypothesis, etc. We are far, far from being able to prove any of those mathematical open problems, and I would love to see it solved. Similarly, in computer science, I would like to see a proof that P is different than NP. So I could give you a long list of challenges given infinite computing power.
So one of the things you didn't mention was power. So power also has to be free or unlimited amount of power.
But
So,
unlimited computing power will solve the energy problem.
I see, that's right. Well, I guess that's going to be my point, is that the way we use our supercomputers today is really to get greater fidelity in the solution. So we can solve a much larger problem, which has greater resolution of the details. So that's one way. The other way is by doing ensemble calculations. So we run multiple sequences of a computation where we adjust the parameters to get an optimal solution. And you can think of that as getting the optimal solution for a car design that minimizes the impact on the user. You want to run many experiments. So high performance computing can do that. So now we can extrapolate and say that we're going to be using this fictitious machine, which has unlimited resources, to give us a situation where we have unlimited computing power to get the most optimal design and to run things at greater fidelity.
For me, it's very simple. I would train the largest neural network that anybody has ever seen on all the data that is available to us, because right now we can't do it. And it did magic the last time when we trained it in smaller data. It'll be interesting.
Anybody else has a wish list?
So what do we do with a dream machine?
Yeah.
Well, maybe I simulate my own brain.
Yeah, I like to use it to actually validate physics models, because I think a lot of equations we write down, they're only approximations, right? They're maybe first order correct, and then we throw out the lower orders that maybe is too much detail and doesn't matter. I really want to see, right, all these things that we just take for granted, is that correct, right? I mean, Newton's law was pretty good approximation until you hit something like quantum scale, right? And so, what can we find, what doesn't fit, right, with reality to the precision that we need? I think that would be very interesting.
Thank you. Thanks for the question. Yeah, so.
Okay, so thanks for sharing. I'm from Hong Kong University of Science and Technology, and I'm doing research about understanding how brain encoding signals using its spike trains, the electrical signals. So we know that the computer is working in a synchronized way with clock cycles, but the brain seems like asynchronized and with low float precision, but very high temporal precision. So I'm wondering that whether this intuition can help us in understanding how how the brain works and how to design supercomputing. Thanks.
Thank you. I think somebody was talking about neuromorphic computing.
Yeah, so I actually looked at this for quite a longer time, and I'm with you. I thought it could do something, but then at some point I realized, well, planes don't flap with their wings, and dogs don't drive on wheels. So maybe the brain just didn't have the technology to work on a in a synchronous way, and it had to work asynchronously, but I don't know. So that's it's not clear. It's great to do research in this area.
Okay, thank you very much.
Okay. I think I don't see any other question from the audience. We have a little bit time, and this is a global young scientist summit. And I think we have this controversy between quantum versus classical. And we have very smart people out here. So I guess I will give each of our panelists a little bit of time to share what you think these smart people should work on in the next decade. So we can start with Adi, maybe.
So I would say that if I had a limited choice of working on one area which seems to have the biggest promise, I would say it's AI. And if I'm expanding it away from computer science into general science, I would say that the biggest challenge we have at the moment is understanding how the brain operates. We have very limited understanding at the level of how one neuron is talking to a neighboring neuron, but we really don't understand the big design principles, how the brain is so successful, using so much energy in order to be so smart.
So if I could just ask, because Torsten was saying that maybe we don't need to understand brain, right? Just like how the birds fly are very different from how the aeroplanes fly.
I didn't say. Let me clarify. I didn't fully say that. But it's not always. Wait. Let me just say. So we at some point we understood the foundational laws of physics. We were able to build better planes than nature through evolution. If we understand the fundamental laws of information processing and of information representation, then we can probably build better systems in biological systems, because every single time in human history when we understood foundational laws, we were able to out-engineer biology. Yet, it's a good idea to follow biology until we understand these laws. So I'm with you. I'm also with you in the spiking thing, but we have to be careful. There are fundamental laws, hopefully.
Okay.
So let me ask the audience a question. How many people believe in quantum computing? Raise your hand if you're a believer. What's a believer? Somebody who thinks it'll happen in the near future, in your lifetime. Your lifetime. Okay, it's a small number. It's not a large number. Okay, so here about what areas to go in. What kind of research should you delve into? So I would say that quantum computing is one area which is ripe for research, right? So it's ripe for understanding, learning, and developing algorithms and ultimately software which would run on some architecture that claims to be quantum based. So I think that's a good area to go into. Even if we're skeptical about quantum computing, developing. Sorry? In the short term, yes. In the short term. Yes, even if we're in the short term. Okay, sorry. I'm looking at the clock now.
So you moved to the quantum side for research.
Well, it's a quantum side, it's what we have seen is, lots of people working in quantum, it started as fundamental research. And then suddenly one day, if the field develops enough, then hype comes in. And that's, you cannot stop. You have to be involved, whatever. If you don't working in the field, if you like or you don't like, it doesn't matter, you are in there. And we don't know how to control it. And it's very difficult to control, and more, I think, because, more and more people are interested in development and in technology, new technologies. So new generation, of course, has to cope with this sort of path going through from the fundamental research to the mature technology. And criticism, of course, during the hype, we get a lot of them. And that's a good thing in a sense. So, we learn how to cope with that, I think.
Yeah, I just want to point out that, consider how many people and how much money is dumped into developing silicon, right? And how long of a history we've had, right? Since say Schottky in 1940 something, right? You know, and compared to what the quantum community, right? This is a order of magnitude scale. And so it's a little bit unfair in comparison for where we are right now in quantum to where the semiconductor industry is with the classical computing. But yeah, I think it's a really exciting time, and we should be, I'd love to have more people looking into it, because there are probably a lot of things that we don't know yet. And when people ask me what's the best application for quantum, I say it's probably one that we just don't know yet at this point.
So I'm a little bit torn about the quantum versus HPC thing, as you've probably seen, or the supercomputing thing. And I believe in quantum, we are right now in the era of Charles Babbage, which was the first, maybe a little bit further, but not too much, which was the first digital computer. And so I would definitely not recommend buying a quantum computer today, because they're just not super useful. But I see the potential. So this computational space is potential. So we should really invest our brains into this, into moving forward and making this a reality, and then see what it does. So we shouldn't dismiss it immediately. So I hope to gain some more interest in the audience for it, but I agree today, yeah, in the near future, maybe.
Thank you very much. And I think time's up. So please thank the panelists for very insightful discussion.